Okay, so our last unit deals with a type of reaction that we have talked about a little bit in the past. We're going to talk a lot more about it now, and it's referring to oxidation reduction reactions, and it talks about how the electrons get transferred. So if you remember, one of our driving forces, we had 3 of them in the past. Okay, we talked about a precipitate being formed. We did that not too long ago when we were talking about forming solids, right? If a liquid is formed, that would be acid-base, produces water, or gas is produced. Those are like combustion reactions. So it's been a while since we've done those. So those are the 3 that we've done so far. The 4th one, which we've talked about a little bit, is when electrons are transferred. And everything that we did, which was single replacement, is an example of a driving force where electrons are transferred. And single replacement reactions are a situation where you have an element, so something like, say, aluminum, plus a compound like copper chloride, and it turns into a new element, copper and aluminum chloride. Now I know you guys already know this, or maybe you knew it at one point, you've probably forgotten it by now, but single replacement reactions are kind of a subset of a big category of reactions called redox, or oxidation reduction. Most people abbreviate it as redox. So single replacement reaction occurs because the electrons are transferred from the element to the corresponding ion. So in the example I gave you, I had aluminum and copper chloride. Well, the copper has a positive 2 charge inside there, if you remember how to do Roman numerals, and it turns into aluminum chloride, where it has a positive 3 charge, and copper. So the aluminum, which starts off with 13 protons and 13 electrons, ends up with only 10 electrons. It gives some of those electrons to the copper, which ends up with, I think copper's number 29. 29 protons, 29 electrons. Over here it only has 27 electrons. And so the electrons are given away. That is a transfer of electrons from the element to the corresponding ion. And when it comes to balancing redox reactions, what we're going to do is we're going to look at the net ionic equation. In other words, all we're going to look at is the things like aluminum and Cu2+, change to Al3+, and Cu. That's all we're going to look at. And we're going to look at how the electrons change as the reaction proceeds. And the thing is, we have to make sure the electrons are conserved. You can't have something lose 3 electrons while something else only gains 2. And so we're going to talk about how that applies to balancing. But first we're going to do something called oxidation numbers, and that would be charges. So oxidation numbers are the charge present on each element in either a compound or an ion. It's very similar to what we were doing when we were doing Roman numerals. So the rules are anything that's an element, and when you see it as an element, it's written as aluminum, or it's written as fluorine. Okay, those are elements in their standard states. Aluminum would be a solid, fluorine is a gas, and they have an oxidation number of 0 because the number of protons equals the number of electrons. It's electrically neutral. Same thing here. The number of protons inside that equal the number of electrons total. Okay, and so it's electrically neutral. It doesn't have a charge on it. However, if you have something that's a monatomic ion, so something like Al3+, their oxidation number is whatever their charge is, or F1-, whatever its charge is. But as an element, it doesn't have a charge, so it is assumed to be 0. In a compound, if you have hydrogen, it has an oxidation number of 1+, and that should look really familiar to you. If you remember when we were doing charges, the charge on hydrogen in something like H2O is 1+. And that leads into the next one. If oxygen is in a compound, it has a charge of -2. Now there's an exception to both of those, but you guys don't have to worry about that. There are things called hydrides, metal hydrides, where hydrogen is -1, and there are things called peroxides, where oxygen is -1. That's AP chemistry level stuff. You guys don't have to worry about that. And then anything that's an alkali metal in a compound is +1. And again, that should look really familiar. If you had NaCl, you would assume Na is +1. Okay? Everything else from there, and this is the big rule, the sum of the oxidation numbers of all the elements present in a compound or an ion must equal the charge on the compound or the ion. So that's very similar to what we were doing before when we did Roman numerals. And it is. It's a repeat of what we did. They're just calling them oxidation numbers instead of charges. That's all. So, using the rules for the oxidation numbers, I want you guys to practice determine the oxidation number of each element present in the ions or compounds below. So, for the first one, I'm looking at that. I see an element. I don't see a charge on it. Boom. I'm going to say that's 0. Same thing here. I see an element. One capital letter tells me it's an element, and I don't see any charge on it. Also 0. Easy so far. Down here, this is a compound, and so I have to use my rules based on the oxidation numbers of oxygen, which is -2. Whatever copper is X, but there are 2 of the coppers, so 2X plus -2 has to equal 0. That's our last rule, that the sum of the oxidation numbers has to equal the charge on the compound. Well, that compound does not have a charge. So I got 2X minus 2 equals 0. Therefore, the charge, or the oxidation number on copper, is 1 plus. Now here, you might think that's an element. It's got one capital letter. However, elements don't have charges, like chlorine and the SR. This is a monatomic ion, and its oxidation number is whatever its charge is. Okay, let's drop down to the next one. Inside here, this is a compound. The sum of the charges is going to be equal to 0, but we have to figure out what those charges are. So oxygen is -2, and there's 2 of them. Hydrogen is +1. Those are both of the rules that we've had before. But we don't know what nitrogen is. We're going to call it X. So I've got 1 plus X minus 4 equals 0. X is therefore 3. And it's +3. Now, if you look on your periodic table, you might see something different for nitrogen. And that's because its most common oxidation number is -3. But under the rules for oxidation numbers, you can't use that. You can only use the rules that we have on that previous slide. So here, nitrogen has an oxidation number of +3, hydrogen is +1, and oxygen is -2. Okay, inside here, again, it's a compound, so that means the sum of it is going to be 0. I have 2 times +1. I don't have a rule for sulfur, X. I have a rule for oxygen, 4 times -2. So I've got 2 plus X minus 8 equals 0. X is therefore 6, and that's the value for sulfur. Sulfur's oxidation number is a 6. Now again, if you look at the periodic table, you probably see a -2 written above there. And again, that is the most common oxidation number. However, according to the rules for oxidation numbers, sulfur doesn't have that. So in this case, sulfur is +6. Okay, let's jump down to this one. Now this is not a compound. This is an ion, and the way I know that, it's got a -1 charge. So when I add these guys up, it's -1. So if I'm going to use the rule for oxidation numbers, I have chlorine, I don't know, because that's not one of my rules. I have 4 times -2 for the oxygen equals -1. I have X minus 8 equals -1. In this case, chlorine is +7. Okay, again, not on the periodic table, but according to the rules for the oxidation numbers, it is +7. Go ahead and see if you can do the SO3 2-. Again, this is an ion, so that means the sum of it is going to be -2. Alright, so if you add this up, you got X for sulfur, 3 times the rule for oxygen, which is -2, equals -2. I've got X minus 6 equals -2. X is therefore +4. For sulfur, a different number from a previous one. Sulfur has a lot of oxidation numbers, actually. So does chlorine, for that matter. So you're going to see things bounce around a little bit. You just kind of have to get used to that and use the rules for oxidation numbers. So inside here, this is a compound. That means the sum on it is 0. Okay, potassium is one of our rules. It's an alkali metal. So it's 3 times +1. Phosphorus is not in our rules. And then oxygen, obviously 4 times -2 equals 0. So we got 3 plus X minus 8 equals 0. Phosphorus is therefore +5. And again, it happens. Sometimes oxidation numbers, particularly for the nonmetals, they bounce around a little bit. Kind of like our Roman numerals did with the transition metals. They bounce around a little bit. So that's the oxidation number of phosphorus. Oxygen would be -2 and potassium would be +1. This last one I didn't put in the homework because it's complicated. if you recognize CO3, you might recognize this as carbonate. There are 2 of them. 10 we don't know. Adds up to 0. So what you get is you get 10 is positive 4. Okay, so that's kind of what we did before. But then you still have to figure out inside there what C is. So you have positive 4 plus x plus 3, oh, no, I lied, 2x, and 6 times negative 2 equals 0. So you got 4 plus 2x minus 12 equals 0. Add the 12, divide by 2, subtract 4, whatever. You end up with carbon being positive 4. Okay, like I said, I didn't put one of those in the homework, and if I had known this was in here before I did the movie, I wouldn't have done it. But the big idea is you have to follow the rules to figure out the charges of every element in a compound or an ion, and it might be different from what you expect.